You've maybe heard the words exothermic and endothermic before. What's the difference between them? What does that have to do with these energy changes that we've been talking about? So let's look at these in two terms in more detail. Whenever heat is transferred, it is either absorbed or released. We call a reaction or a change endothermic if energy is absorbed in the reaction or changed. And when energy is absorbed, we have a positive Q value. On the other hand, in an exothermic reaction, energy is released in the reaction or change, and you end up with a negative Q value. So let's look at endothermic reactions in more detail. This is called a reaction pathway diagram of an endothermic reaction. In this reaction pathway diagram, you can see that the products have a higher potential energy than the reactants. That's what makes this reaction endothermic, that the products are higher in potential energy than the reactants. As the reaction progresses, we go from reactants to products. Reactants are what you have the start of the reaction, and then you produce products at the end of the reaction. So in this example, we might be looking at the thermal decomposition of aluminum oxide into aluminum and oxygen gas. And if we put kind of numbers on this graph, we can see that we could actually use the graph to measure the energy change. So it would be a way of graphing those Q values that we were just calculating earlier. Here, if we look at these values on the graph, we go like with 50 joules, 100, 150, 200, 250. We can use these values to calculate how much energy is absorbed when you go from reactants to products. So just like with temperature, we do final minus initial. So if we end with 100 joules of potential energy in our products, but we started with 50 joules of potential energy in our reactants, then the difference here is a positive 50 joule change energy absorbed in this endothermic reaction. So the Q value for this reaction is this positive 50 joules as we go from reactants to products. Notice that that's not the only thing on the graph. We also have this weird EA thing here. This is activation energy. And activation energy is the energy you need to put into a chemical reaction in order to just kind of start things off, to help the first bonds get broken to actually start the chemical change, the chemical reaction. We can also use this reaction pathway diagram to calculate the activation energy. How much energy do we have to put in to get this chemical reaction to happen? Again, we look at the peak value. Here is 250 joules. And we subtract our starting value, which is 50 joules. So this is kind of our initial value, and this time our final value is up here at the peak. So the activation energy is going to be that 250 joules minus the 50 joules that we started at from the reactants, and that gives us a difference of 200 joules. So the activation energy, the amount of energy you have to put into this chemical reaction to actually even get it started, is 200 joules of energy. With endothermic reactions, it's important for you to realize that energy is transferred from the surroundings into the system. From the surroundings into the system. Because of that, if heat energy is moving from the surroundings to the system, that makes the potential energy of the system increase, but you can't get something for nothing. You can't magically make energy appear out of nowhere. That energy has to come from somewhere. Where does it come from? It comes from the kinetic energy of the particles in the surroundings. The potential energy of the system increases, but the kinetic energy of the surroundings decreases. So the temperature of the surroundings drops. The endothermic reactions feel cold. That's going to make them different to exothermic reactions, as we'll see next. So let's look at exothermic reactions. Here we have another reaction pathway diagram. And here you can see that products have a lower potential energy. They're lower down on the graph than these reactants are. So this is some kind of exothermic reaction, maybe like the reaction between hydrogen, liquid hydrogen and liquid oxygen to make water and vast quantities of energy. This is rocket fuel, basically. If we label the graph with some values, then we can actually use the graph again to calculate activation energy or to calculate Q for the reaction. So let's do Q first. Our products are our final state in the reaction, and our reactants are our initial state of the reaction. So if we want to calculate Q, we need to do the final value minus the initial value. So 60 joules minus 120 joules. And we see that our Q value is negative 60 joules. I mentioned earlier that exothermic reactions have a negative Q value. And here you can see that this is in fact true. The activation energy in this example, we want to do the same thing that we did before. This is now, if we're measuring activation energy, then this is the final point in the calculation. But our initial point is still the reactants. So our final point here is at 300 joules. And subtract my initial value, which is 120 joules. And I get a value of 180 joules. Notice that even though this is an exothermic reaction and my Q value is negative, my activation energy is positive. Activation energy is always positive. Getting a reaction started always requires adding energy to the reactants. It's an endothermic process always to get a reaction started. In exothermic reactions, energy is transferred from the system to the surroundings. Again, you cannot create or destroy energy. So what happens is that the potential energy of the system decreases. That energy can't just disappear. Where does it go to? The kinetic energy of the surroundings increases as a result. Because of this increase in kinetic energy, remember kinetic energy, temperature is a measure of kinetic energy. Because the kinetic energy of the surroundings increases, exothermic reactions feel hot. So think about burning something. That's the most common example of an exothermic reaction. Those feel hot. You warm your hands by the fire or whatever. Because the potential energy lost by the reactants has to go somewhere. It goes to the surroundings, and that's why these exothermic reactions feel warm. So just to summarize some of the definitions that we saw in those reaction pathway diagrams. If you want to calculate Q using a reaction pathway diagram, what you're doing is you're calculating the quantity of energy released or absorbed during a chemical reaction, and you have to do the potential energy of the products. This is what you have at the end, the final part of the chemical reaction, minus the potential energy of the reactants, those initial values that you have. Similarly, for activation energy, this is the energy barrier or hump that must be overcome to start a reaction. And to calculate this, you do the potential energy of the peak of the reaction. So the top of that hill, this is the peak, minus the potential energy of the reactants, whatever you had at the start of the reaction pathway. So let's do some examples. Is this reaction endothermic or exothermic? The reaction is endothermic because the products have a higher energy than the reactants. Use the reaction pathway diagram to determine the heat of reaction for the above reaction. The heat of reaction is the Q value. So we want to do the products, which look like they have a value of 300, minus the reactants, which have a value of 100 joules. So we'll do 300 joules minus 100 joules gives me an answer of 200 joules. Use the reaction pathway diagram above to determine the activation energy for the above reaction. We want to go from the top of the hill to the reactants. So we're going from 400 joules to 100 joules, and that is a difference of 300 joules. You can make sure you've gone in the right direction because remember, activation energy is always positive, so you should always end up with a positive value for this calculation. So let's summarize what we've learned about exothermic changes and endothermic changes. We've just talked about exothermic, so we'll start with that one. Exothermic changes. Exothermic reactions feel hot because heat exits the reaction. Exothermic, exit. They both have that X in it. Because energy is released, energy is transferred from the system, from the chemicals, to the surroundings. The products will have a lower potential energy than the reactants. Therefore, the Q, the heat energy, is negative for the system, for the chemicals. Endothermic reactions, on the other hand, they feel cold. Heat goes into the reaction. It's like if you're holding it, it's like sucking the heat out of your hand. Heat goes into the reaction because energy is absorbed. Energy is transferred from the surroundings into the system, into the chemicals, which then increase in potential energy. Therefore, products have a higher potential energy than the reactants. And that's why Q, the heat energy, is positive for the system, for the chemicals. I hope this helped.